Alright, calculus. So, sorry that I haven't done a video in a long time, but doing it again. So, starting up in chapter 3. So 3.1 had to do with derivatives. I know you guys already know, like, the shortcut, where if I were to ask you to find the derivative, you know it would be 2x. But for the sake of understanding how we got that, we're going to do the long way, which is just proving that the shortcut will work. So the first problem that we did in class said limit as h approaches 0. Now this is how we find the derivative. It's kind of like the change in y over the change in x. So we have here f of x plus h minus f of x over h, and that's the limit as h approaches 0. Now notice if you plug in 0 right now, you're going to get undefined, but there must be something that we can do to work this problem out. So we're going to try to find the derivative of x squared using this formula. So what we're going to do is we're going to find the limit as h approaches 0. Now what we're going to do is we're going to take x plus h and plug it into wherever x is. So in this case, you have x plus h squared. It's like you're putting it in place of minus f of x, which we know is just x squared, over h. So now we're going to do some simplifying so we can get rid of that h right there. So if we were to FOIL out right here, we'd have the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared. Okay, all over h. And remember, a parenthesis squared, if there's a plus or minus in between, it's not x squared plus h squared. Don't do that. Don't forget about your middle term, 2xh. Multiply these and double it. Okay? But now you'll notice here that you have x squared minus x squared, because that'll cancel out. And now I can actually reduce an h from the remaining terms. So this goes away on the denominator, this h goes away, and this just becomes h to the first. So now I can rewrite this as the limit as h approaches 0 of 2x plus h. So now when I plug in 0 in for h, all I'm left with is 2x, which we said, again, by the shortcut rule, we would get 2x anyways. So again, this is the proof to show that when you take the limit as h approaches 0, when we use this identity right here, that we can actually come to our shortcut answer, okay, 2x. So that was our first one. Now the other one looks like this. The other one we did in class, so we have the limit as h approaches 0, or we can do the limit as x approaches a of f of x minus f of a over x minus a. This is even more so like slope, you know, y2 minus y1 over x2 minus x1. So the problem we did in class for this one, we said f of x is equal to the square root of x, which if you do the derivative correctly, f prime will end up being 1 over 2 root x. So that is what we should end up with if we apply this correctly. So the first one says plug in x. So remember, we're always talking about the limit. Limit as x approaches a of root x minus, it says plug a into your f of x, so minus root a over x minus a. Now, just like we plugged the 0 in for h, we can't plug the a in for x right here, because that gives you a minus a, which is 0, which makes undefined, that's not the answer. There must be some way we can simplify this. So you've been taught so much about rationalizing the denominator, getting roots out of the denominator. Well, actually, in this case, we're going to rationalize the numerator. And the way you do that is by multiplying it by itself. Just switch the symbol in the middle. Okay? Because when you do that, if you were to FOIL the top, you'll notice that the outer and the inner, since it is a positive and a negative, will actually cancel each other out. So therefore, if I were to actually distribute this, actually I'm going to write it here, the limit as x approaches a, root x times root x is x, negative root a times positive root a is just negative a, and on bottom we're left with x minus a times root x plus root a. Okay? And notice here, top and bottom, you have the same parentheses. Those cancel out. We're left with the limit as x approaches a of 1 over root x plus root a. Now we can go ahead and plug that in. Plug a in for x. So you have root a plus root a, which is 2 root a. So 1 over 2 root a, which, switching the variables, actually ends up being the same thing. So that is how we use this way right here. Okay? So good luck with that. And the one final thing that we went over is being able to graph the derivative of the original graph. So if I show you f, if I give you some graph here, okay, where this is 1, 2, 3, 4, 5, 2, 3, 4. Now I can't remember specifically. I'm going to assign values. It's not going to be the same one in class, but whatever, you'll get it. So let's go here, here, and here. Okay? So we have, alright, so I'm going to say now, this is the graph of f. So what we're going to do is we're going to assign slopes here. The slope at any peak or valley is going to be 0. So the slope here we say is 0. The slope here we say is 0. Let's say right here, the slope is 1. M equals 1. If I were to say the slope here is m equals negative 1. Okay? Let's say the slope at this point, actually let's make this 1/2. The slope here, m equals 1/2. And we'll say right here at the very beginning, m is equal to 1. Okay? And lastly, m equal to 1. Hypothetically, okay? Just assign values off the top of my head. So we're going to use these slopes to graph the derivative. Okay? Do I have another marker? No. Okay. So I'm going to draw another graph here. One, just a slightly smaller to scale. 4, 5, 6. 1, 2, 3, 4. So this will be f prime. So what you're going to do is you're going to graph the slopes of f. Those values will become your y values for your derivative. So when x is 0, it says your slope is 1. So when x is 0, your y value is 1. When x is 1, your y value is 1/2. Okay? When x is 2, it says your slope is 0, so your y value here is 0. When x is 3, it's back up at 1/2. Or sorry, that would be negative 1/2. My bad. It's going down. Negative 1/2. At x equals 4, it says your slope is negative 1, so your y value is negative 1. Right here at x equals 5, your slope is 0. So your y value is 0 at x equals 5. And then lastly, at x equals 6, your y value is 1. So there you go. So we have this graph here. It's going to make a little curve right there. So that is how you draw that's how you graph the derivative. Is find the slopes at these given points, and those become your y values for your derivative. Okay? So good luck with those. You'll be able to tell where, again, your slope is 0 by the peaks and the valleys. Let that help you match up the graphs for the homework. Alright? So good luck with that. That's our first video for Calculus 3.1, alright? Actually, it wasn't our first video, but it's my first video in a while. Good luck with that.